Hi students, this is going to be part 1 of chapter 2. This chapter will span several segments. Chapter 2 is all about chemistry, specifically chemistry as it relates to biology, or in our case, microbiology. I hope that some of this sounds somewhat familiar to you, but if it's not, then just be sure you spend a little bit of extra time to get the basics down. We will be using a lot of the information about chemistry in several of the upcoming chapters, so it's important not to delay working to understand and remember this information. You want to have the foundation to understand material in later chapters, like, for example, the metabolism chapter. If you don't feel comfortable with chemistry after we've gone through the lectures, I urge you to please visit the Star Center, go to supplemental instruction sessions, or ask me questions. But please, get it straight. Don't put it off because you feel a little frustrated. Feeling a bit confused is the prelude to actually learning, so just embrace it, try to dig in. Seek guidance when you need it so you can stay on top of the material. I want to alert you to the fact that I don't intend to speak as a chemist. I'm going to hopefully make this a little bit more understandable to those of you who have not yet taken your college chemistry course, and it's been some time since a high school chem class. I'm going to speak maybe a little bit anthropomorphologically. I'm going to talk about atoms as being happy, which of course they can't be. They're just atoms and they don't have emotions. If you've recently had chemistry, this will very likely be a review on a simple level for you. Perhaps you can use your experience and knowledge to assist your classmates who struggle a bit more with this. All right, gonna dive in. Some of the terms that are important. Matter defines anything that takes up space. Atoms are the basic unit of matter. We will be looking at subatomic particles, but only to the level of nuclei with the protons and neutrons, as well as the electrons in the orbitals or the shells. We're not going to be going so far as to look at things like quarks or whatnot if you were a physicist. So we're going to look at an atom at the level shown here, with the nucleus containing protons and neutrons. Neutrons have no charge, as indicated by this little n with a 0. Protons have a positive charge, and electrons, which are orbiting the nucleus, have a negative charge. We'll be talking more about this as we move through the chapter. When we're looking at an atomic structure, I have loaded into this slide an image that I took from the internet. It's not your text. It's really a good example of one of the entries of the periodic table. It has some of the numbers that are important, that are associated with that particular element. You may now wonder, what exactly is an element? An element is composed of a single type of atom, such as cobalt, depicted here in the example. Cobalt is not one of the more important elements for life, but since it was a good example of the periodic table entry, I used it here. An element is a single type of atom, and the atomic number is a number that is associated with that particular element. The atomic number is equal to the number of protons. The atomic number is a very important number. You see that it's 27 for cobalt. 27 corresponds to the number of protons in the element. It's not going to change. If you change that number, you're going to change the element. The position in the periodic table is dictated by the number of protons, and that's going to reflect the atomic number right here. The atomic mass is essentially the atomic weight, and it reflects the number of protons and neutrons. The electrons are so small as to not to register any mass on the scale we're dealing with. Protons and neutrons are reflected in that atomic weight there at the bottom. You may wonder, why is it that we have a decimal place in the atomic mass? Don't protons and neutrons, aren't they whole numbers? In some, yes, but this reflects an average. I'm going to briefly mention now that there are different isotopes. We'll come back to that in a minute. This mass number reflects an average of the variety of atoms that are out there in nature. The atoms may differ in the number of neutrons and still be the same element. The mass is a reflection of the protons and the neutrons. Finally, I'll mention that over here on the far right, you see some numbers, and this is reflecting numbers of electrons. That will be in the electron shells. In this class, we're not going to pay much attention to that. Many of the periodic tables don't even include this. This entry does. What is important to realize is that when we're thinking about the elements, there's really a minority of them that are abundant in life. There are more that are necessary but are less abundant. 92 elements from the periodic table are common on Earth. The periodic table describes more, but only 25 of those elements are essential to life. If you look even amongst those 25 elements, there are really about 4 of them that comprise 95% of the matter in living organisms. Those 4 are carbon, depicted by the C, hydrogen, depicted by H, oxygen is the O, and nitrogen is the N. So these 4 comprise 95-ish% of the living matter. Then there are some other elements like calcium, potassium, phosphorus, sulfur that comprise a lot of the rest of the 4%. In addition, there are what we term trace elements that are still essential. Things like iodine or magnesium, zinc. Those elements are also necessary for cells, but in very small amounts. Thus, trace. In here, we will spend most of our time talking about 6 elements. We'll come back to that in a moment. A moment ago, I mentioned that there are such a thing as isotopes. Let's define those better. Isotopes are a given element that differ in the number of neutrons in their nuclei. Here we can use carbon as the example to explain this concept. First, you should realize that there are stable isotopes, which means they exist basically forever in that form, and there are unstable isotopes, which tend to be radioactive. Radioactive elements decay, and they potentially become a different element. If you've been around science a little bit, you've maybe heard of things like carbon-13, carbon-14, perhaps you've even heard of carbon dating. What does this all mean? Carbon exists in 3 isotopes. Carbon-12 is the most abundant, and that's the form most common in our bodies and other living cells. But there are also small amounts of isotopes carbon-13 and carbon-14. These isotopes have additional neutrons in their nuclei, hence the larger designation. Isotope numbers are a reflection of the individual atomic mass of these different varieties of carbon. Isotopes carbon-13 and carbon-14 have additional neutrons compared to the more abundant carbon-12. They are also radioactive. If you are curious as to how carbon dating works, this is a brief explanation. Carbon-14 is a radioactive isotope that will decay. In life forms, the amount of carbon-14 that is present is pretty much consistent as a ratio of carbon-14 to carbon-12. As long as the organism is living, they're incorporating carbon into their structures, into their body, and there'll always be that same amount of carbon-14 relative to the amount of carbon-12. As soon as the organism stops metabolizing because it died, then carbon-14 is no longer being incorporated and it's going to decay and disappear. You'll only be left with the stable carbon-12 and lesser amounts of carbon-14. It's a calculatable timed decay. When examining a once living organism or fragment of an organism, even something like a piece of wood, and determining how much carbon-14 is left in relation to how much carbon-12, you can then estimate fairly accurately how long ago that particular thing was alive. Of course, there's a limit. Eventually, the carbon-14 is pretty much all gone, and then you can no longer accurately date something. So I think they're fairly good at getting something's age up to about 60,000 years, maybe a little further with better and more sensitive techniques. But at a certain point, there's not enough carbon-14 to measure. If something is like 200 or 300,000 years old, it can't be accurately dated because the carbon-14 has disappeared. So in sum, this idea that isotopes are the various forms of a particular element. They vary in the number of neutrons. In this example, we examined carbon isotopes. Remember, the number of protons will not vary. or you are then considering different elements. Next, let's talk about electrons. Electrons are the negatively charged particles that are orbiting the nuclei of particular atoms. Really, it's the electrons that we're most interested in when we're considering a particular atom. This is because it's the electrons that are going to determine the bonding capacity. Bonding between atoms forms molecules. The nuclei are not involved in bonding. The electrons are. The electrons interact to form bonds, and there are 3 types of bonds we will discuss later. Electrons occupy what we call electron shells. The most important electrons are the valence electrons. Those are the electrons that exist in the outermost shell. The valence electrons are the ones that are going to potentially interact with electrons of another atom. In this particular figure from your book, you can see that these orbiting electrons are depicted in different ways. We're going to spend the most time looking at this type of ring structure down below. I think it is easier to understand for our purposes. You can visualize electrons existing in layers. The outermost electrons, the valence electrons, are depicted here in the outermost ring. In reality, that's not how electrons exist. They're not orbiting around like planets around the sun. They're in cloud-like structures around the nucleus. This flowered type shape believed to be closer to reality. You can see in this outer area the rings kind of superimposed on top of the orbitals. While this 3-dimensional structure or the 3-dimensional depiction might be closer to what's happening in life, it's not that easy to visualize the valence electrons. So we'll spend our time looking at the ringed electron shells like down at the bottom. If you're curious, your textbook has a lot more description about orbitals, and you can dig into those. When you take chemistry, you'll spend a lot more time discussing them, but we can't. We're going to briefly describe them and spend a little bit of time looking at these ring-like structures representing orbitals. Furthermore, we're only going to spend time considering the first 3 rings. That will cover enough for our purposes. So let's talk a little bit about the first shell. The first layer of orbitals only has room for 2 electrons. As you move out, the second shell now has room for 8 electrons. It's depicted by these little red-orange kind of dots. When you combine them, you can see what it might look like in that configuration at the end. The nucleus is in the center, and then you have the first ring with 2 electrons, and the next ring has room for 8 electrons. This is how we will be depicting the electron shells in order to represent what's going on with these different elements, the different atoms. Now, the periodic table is quite large. If you look at this, the top of this particular figure, you can see that we're missing a lot of the periodic table. We're only concentrating on the highlighted areas, which are now blown up down here at the bottom. The simplified version of the periodic table is used here so that we can understand how the periodic table is set up. The table setup itself can be informative about the elements because where they are placed gives us clues about how they behave. Let's take a look here. Hydrogen is our simplest element. It's most often comprised of a single proton and a single electron. For hydrogen, there's one single electron orbiting that outer shell. 1 proton, 1 electron is the typical makeup of the atom hydrogen. But if we jump to the second element, it's on the other end of the table. This is helium. It has 2 protons and 2 electrons. For helium, now that outermost shell, which is only the first shell, is filled. There's no more room in the first orbital or shell for electrons. The first shell holds only 2 electrons. Let's jump to the next atom on the table, lithium. And consider the one below lithium, which is sodium. Sodium has a symbol that might not be obvious. It's Na. But let's take a look at what we notice about the outermost orbital in these two elements, lithium and sodium. If we look, lithium has one single electron right here. And so does sodium. These elements have one single electron in that outer shell. If you jump again over to the other side, if we look at the elements under helium, their electron shells are completely full. But back up one column. Look at something like fluorine and chlorine. We'll notice if we're looking at the outer ring that there's room for just one electron. That's important. We're going to come back to that idea when we talk about specific types of chemical bonds. This one, an ionic bond. We're going to be looking at bonds that are occurring between this second to last column in elements and the first column. The elements in the first column, things like helium, the elements in the very last column, things like helium and neon, they have their outermost electron shells completely filled, and it makes them quite, or quote unquote, happy. These elements are happy when their electron shells are full. The elements in the last column are sometimes called the noble gases. They're really not that important to life because they don't tend to form any molecular bonds at all because they don't need to. Their outermost shells are completely filled up. We're going to be spending time looking at the other elements in the other columns. Just like people, elements try to be happy, and so they try to fill that outermost shell if it's not already filled. They fill them by making bonds with other elements and form molecules. We're focusing on this area here on this periodic table because this is the area where most of the elements that are important to life exist. Remember I mentioned things like carbon, extremely important to life, hydrogen, oxygen, phosphorus, sulfur, sodium, potassium, nitrogen. These are all elements we're going to be spending time on in the next several chapters. They all belong into this area of the periodic table, thus our focus on this part of the table. We're now going to talk a little bit about chemical bonding. As I was mentioning, the outermost electrons, the ones in the valence shell, are the electrons. The valence is referring to the combining capacity of the atom, meaning whether or not it's going to form bonds. In chemistry, you'll spend more time on this than we will. We will just summarize it. The valence number is going to, for a particular element, be positive if it wants to give up electrons, or negative if it wants electrons. The element will be stable, or the molecule will be stable, when the electron shells are full in the outermost shell. Chemical bonds are when atoms combine together to share or transfer those valence electrons. A molecule forms when two or more atoms are held together by the chemical bonds. The term compound refers to a molecule that has more than one type of element. An oxygen gas molecule, shown right here, this is not a compound. It's a molecule, but because it has two atoms of oxygen bottomed together, which are the same type of atom, it's not a compound. Water would be a compound because of the oxygen and hydrogen, two different types of elements that have bonded. All right, this is a good place to pause, so I'm going to stop here. We'll pick up part 2 on the next video. Catch you on the next one.